Hello everyone. Today we are going to discuss the inverse Z transform through direct integrations. That integration is the complex integrations. It is very much useful to find the value of x of n at some particular value of n. Right? So let us discuss. So first of all, we know that x of g is equal to summation k minus infinity to infinity x of n g to the power minus n. This summation you have to the variable k, right? Variable k, because we have the summation from k minus infinity to plus infinity. So now multiply x of g with g to the power n minus 1 and integrate over the contour in counterclockwise directions. I will come back to that contour later on. What is that contour? K equal to minus infinity to infinity x of k g to the power minus k and g to the power n minus 1. Then integration, you have multiplied, means you have to integrate the same way. Okay. Now, as you know that contour is inside the ROC, because in G transform you have an ROC. This is the circle G magnitude of G equal to 1, and let's say you have a ROC here, and the contour should be inside the ROC. So as these integrations, that is the G transform is converging, right? So we can interchange, because this x of z should converge in the ROC. That ROC indicates itself is the region of convergence. So we can interchange the summation and integrations. Summation is for the k and integration over the contour, and okay, I forgot to write the dg. Then integration g to the power minus n minus k minus 1 dz. So we know the Cauchy integrals theorem. Cauchy integral theorem that 1 upon 2 pi j and complex integration in counterclockwise direction g to the power n minus k minus 1 dg will be equal to 1 for k equal to n, 0 otherwise, that is k not equal to n. Just check, when you put the k equal to n, so it is simply g to the power, that is minus 1, that is 1 upon g, and you can find this complex integration, that value will be 1, because already we have divided by 2 pi j. And if you don't have the k equal to n, then it will be 0. You can check it. So if you do so our integration becomes, so for only k equal to n, this is 1, all the other case it is 0. That means x of n, the right side of this equation, let's say the equation 1, right side of this equation 1 will be n into 2 pi g 2 pi j, which is equal to complex integration c x of z to the power n minus 1 dg. So we have x of n is equal to 1 upon 2 pi g complex integration x of z to the power n minus 1 dg. This is the very important relations to find the value of xn by direct integrations. So these expressions look maybe you maybe are frightened by looking at this equation initially, but it is very simple equation. It is, in other words, we can say that summation of this xn is equal to summation of residues of poles of x of z to the power n minus 1 inside the ROC, inside the contour, not ROC. ROC is the bigger region, contour is a circle only. So inside the contour. So from the basic of mathematics, that is the complex integration, you know how to find the residue of poles. So let's say function is h of z. It has one poles at g equal to g naught, that is single pole, and another pole at g equal to g1 of multiplicity of k. Okay, multiplicity of k. That means in general some other terms. So you have f of z upon g minus g0 and g minus g1 to the power k. Somewhat like this. This is the general expression for some other terms in the h of z. So residue of g equal to g naught is simply calculated as g minus g naught h of z evaluated at g equal to g naught. Okay, so if you have multiplicity of k, multiplicity of poles at g equal to g1, that k times the pole existing. For k equal to 2, twice, that is the g minus g1 square, that is 2 poles at g equal to g1. So residue at g equal to g1 is equal to c, this expression 1 upon k minus 1 factorial d of k minus 1 dg of k minus 1 your g minus g1 to the power k h of g evaluated at g equal to g1. That means suppose there is a multiplicity of 2, then 2 minus 1 factorial, that is 1 factorial, that is 1, and first derivative 2 minus 1 1, so d upon dz and of g minus g1 square h of z. We'll see with the example. Let us we have two complex function f1g equal to g upon g minus 1, and another one is the g minus 2 square. Find residue at all the poles. So residue at g equal to 1, one pole at g equal to 1, so single pole, so g minus 1 f1z evaluated at g equal to 1, so g upon g minus 2 square evaluated at g equal to 1, that is 1 minus 2 square, that is 1 upon 1, which is 1. Then next, residue at g equal to 2 is equal to multiply g minus 2 square f1z and 1 upon 2 minus 1 factorial d upon dz, which is 1 by 1 upon factorial d upon dz 1 g upon g minus 1 evaluated at g equal to 2. So take the differentiation evaluated at g equal to 2. Take the differentiation of this, so g minus 1 into 1 minus g upon g minus 1 square. Okay, so g minus 1 minus g upon g minus 1 square, that is minus 1 upon g minus 1 square. So put the values to minus 1 upon 1 square, that is 1, that is minus 1. Let us move the, let us discuss some example. So given that x of z is equal to 1 upon 1 minus half to the power g minus 1. By simple looking at this, you can easily say that it is half to the power n un, provided that it has been given magnitude of, that is ROC, magnitude of z is equal to greater than half. And you can find out the values at for example x of minus 2, sorry, x of 2 minus 2 will be 0, obviously x of 2 will be the half to the square, that is 0.25. okay, and x of minus 2 will be 0. We need to prove this through direct example. Clear? Let us move. So x of z is equal to g upon g minus half, right? Now to find the x of 2, first x of 2, we need to do integration contour x of z and g to the power n minus 1, that is 2 minus 1 dj, and contour should be inside the ROC. So first draw the ROC. Our ROC is the magnitude of z greater than half. Always it is a circular ring. ROC pattern is the circular ring. So g equal to 1. So this is your half. So this is your ROC. This shaded region your ROC. This is your half. So your contour should be like this inside the ROC. So put these values. X of z is equal to g upon g minus half. So it becomes g square upon g minus half and dg. Now see here. Okay, there is a 1 upon 2 pi j, right? Yes, 1 upon 2 pi j term. What I have told, this is simply the residue at, because see, whenever I put the contour in counterclockwise direction in the ROC, I see that my pole at half, that is 1 by 2, will be inside the contour. By half is here, and your contour is inside the ROC, so half will be inside the contour. So the pole will be the only pole is existing z minus half or z equal to half. So residue of this function at z equal to half will be the simply z square evaluated at z equal to half. That is, so you write residue of this function, because residue of, I have already told you, just see here, summation of the residue of poles of x of z to the power n minus 1. Here x of z and z to the power n minus 1 is the z square upon z minus half. So residue of the poles inside the contour will be this pole z equal to half. So residue of these functions, or residue of this function at pole g equal to half, which is equal to g square evaluated at g equal to half. So that is 1 upon 4, 0.25. Clear? Now we need to find the x of minus 2. Same 1 upon 2 pi j contour x of g to the power minus 2 minus 1 dz. So here x of z equal to g upon g minus half. So put these values, 1 upon 2 pi j contour is inside the ROC. So x of z is equal to g upon g minus half. So g of minus 2 upon g minus half dz. But now g become a pole for this together, that is inside the integral, that is 1 upon g square and g minus half dg. Now you have one pole at g equal to 0, another, that is a multiplicity of 2 pole, okay, and another pole at g equal to half. So which is simply sum of the residues of the poles. So poles here at g equal to 0, which is multiplicity of 2, right, like this, and g equal to half. So residue at g equal to half will be the 1 upon g square evaluated at g equal to half, plus residue of these functions at g equal to 0 is the multiplicity of 2. So we'll use 2 minus 1, 1 upon 2 minus 1 factorial, that is 1, and d of dz upon 1 upon g minus half evaluated at g equal to 0. So this becomes 4, right? Half square is 1 upon 4, so it comes to the numerator. So 4 plus, differentiate it. When I differentiate it, it becomes minus 1 upon g minus half square, right, and evaluated at g equal to 0. So 4 plus minus 1 upon 1 by 4. You can see when you put the 0, so minus half square, that is 1 upon 4. Now ultimately you get the 0 as expected. It looks trivial, it takes the longer process in the direct integrations, but it saves a lot of time. Sometimes you may not be able to do the question or find the final result by direct integration. So by looking at the lookup table or partial fraction of the that is algebraic expression, sometimes it will not be very easy. So we'll use the direct integration method. Let us move to the typical example which may appear in the GATE exam. Now see, the impulse response of a discrete time systems given below is Hn, and the system response of the systems found to be H of Z, G transform of the system, or the impulse response or sample response of the, if you take the G transform of that sample response, we call it system response. Need not to worry about system response. H of G equal to, that is, these two are transform, G transform pair, 10 G to the power 4, G plus 2 and G minus half. Okay, and the system is found to be stable. The value of H of n evaluated at n equal to minus 2 each. Okay, so sometimes you may say that ROC has not been given here directly, but ROC has been given. System is stable. You know from the basic of G transform, for a stable system, ROC must includes unit circle. So there are two poles here. Okay, so the conventional way is to, that is, fractionize it, partial fractionize it, then go for the lookup table, then find the H of n, then put the value n equal to minus 2. It will take a lot of time, and you know that in competitive exam like GATE, the time is very crucial. So let us demonstrate how we can find easily with the help of direct integrations. Okay, so as it is, system is found to be stable, so only possible way of the ROC is the, you can easily see here, magnitude of G less than 2 and it is greater than half. This is the case when your ROC will include unit circle. This is your half, that is circle of radius half, and this is your circle of radius 2. So this is your ROC for these questions. So H of minus 2 is equal to 1 upon 2 pi j, complex integration, and contour is inside the ROC. Always remember, the contour, counterclockwise contour should be always inside the region of convergence. H of z and g to the power minus 2 minus 1. So we have 1 upon 2 pi j contour, h of j equal to 10 g to the power 4. Here is the g to the power minus 3. So 10 g upon g plus 2 into g minus half, which is inside the contour. The inside the contour is only the pole is the g equal to half, so which is simply residue at g equal to half residue of these functions at g equal to half, which is 10g upon g plus 2 evaluated at g equal to half. In the numerator it is 5, so half plus 2, that is 5, which is equal to 5 upon 5 by 2, that is 2. How easily we could get the result. This is the technique you should use. Now you see another example, okay, so that you can be dead sure with the application part, and more example you can try yourself. So G transform of a sequence x of n is given by this, and if xg converges, obviously if xg does not converge, then we don't have any value for that. That is, xg does not exist. If xg convergence means, what does it mean, xg convergence? Okay, there is an ROC, there is an ROC existing. Otherwise the xg itself is not existing if it does not converge. Xg converge means it has an ROC. So how we can get an ROC for this case? So this is the, if we make only right sided signal, okay, sorry, if xg converges for g equal to magnitude equal to 1, that is unit circle included in the ROC. That means we have only one case where your unit circle is included is the g greater than half and less than 2 or 3, less than 2. Okay, and you know, if I make the less than 3, then ROC includes a pole which is against. The ROC should not include a pole. ROC is the, all the poles will be at the edges of the or outside the ROC, but not inside the ROC. So this is the case. Now for this case you need to find un, then for partial fractionize it, then find the un, x of n, and then put the value of -18, you will get the result. So see how directly we will be getting it. Same way, x of n is equal to 1 upon 2 pi c, 2 pi j, counterclockwise integration, contour is inside the ROC, z to the power 20 upon g minus half and g minus 2, g minus plus 3, okay, plus 3, this is a minus 18, n equal to minus 18, so g to the power minus 18 minus 1 and dg, so 1 upon 2 pi z contour g, minus 19 and 20 change, that is g minus half, g minus 2, g plus 3. When we have the ROC, first draw the ROC here, as it is given that unit circle is in the ROC or ROC converges or G transform converges at G equal to 1, that means it includes the ROC. This is your half circle and this is your 2 circle, so this is your common ROC. So whenever you have a contour inside the ROC, only this pole is in the inside the contour, so that means residue at pole G equal to half, which is equal to G upon G minus 2, G plus 3 evaluated at G equal to half, that is half upon half minus 2 into half plus 3, which is equal to half upon, that is minus 3 by 4 into 7 by 2. So 1 2 to cancel, that is 4 upon 21. See how much time we have saved. So here, to summarize whatever we have learned, that is the concept of we need to find the to apply the direct integration method. We have to learn the concept of complex integrations, knowledge of pole zero, and ROC concept, right? These three things, and also system concept, because we are considering here the system, that is the discrete time system. Obviously we need to know that. Hope you have understand, and let us see how you can going to apply in the competitive exam. See you in the next class.